All right, welcome everyone. Today we're going to discuss some of these vector calculations that can support some of the work that we're going to see in like physics classes and then electromagnetism, some fluid dynamics, okay? But also some of the different integrals, triple integrals, double integrals that we're going to work with as we finish out this vector calculus chapter in our discussion, okay? So let me go ahead, start to share the doc cam, and we'll get going with our next discussion. In this session, we're looking at the curl and divergence, okay? And so as we start to work on this, we'll start off in discussing, okay, we will work with a vector field, f, given by, right, our function p of x, y, z, in the I component, q in the j component, and r in that k component. Okay, so we'll have our function vector field depending on x, y, and z, right, with our functions p of x, y, z, q of x, y, z, r of x, y, z in those different coordinate directions. Okay, and we're going to use the kind of gradient vector, or this what we'll call del operator, right? That inverted triangle and that kind of upside down delta. This del operator, which is going to be this kind of vector where we have our partial with respect to x, partial with respect to y, partial with respect to z in those components, or the same I d dx, j d dy, and k d dz, those components. Okay. Before we had looked at this one to be, right, del f or grad f to be that vector, the partial of f with respect to x, the partial of f with respect to y, that partial of f with respect to z. That's what we had done looking at the gradient vector before, but now looking at this kind of this operator, okay? And so we're going to see how this del operator can interact, right? These derivatives can interact with our vector field to get these two kind of measurements with our vector field. Sorry, get my mouse cursor out the way. There we are. And so first discussion is going to be the curl. And so the curl of a vector field is a measurement kind of as a vector, this kind of vector result of the kind of desired the use of the rotation of particles around a point. Okay, so this discussion here is kind of measurement of the rotation these particles experience around a point. Okay. I kind of think about it kind of like whirlpools in a body of water. We'll have this point, x, y, z in space, right? And maybe the water is flowing. Okay, this is our direction of water flow. And so we'll calculate this quantity, this curl, and it's going to give us a vector, okay? This curl of our vector field F at that point. And it kind of measures, like if we think about our right-hand rule, we have that vector, we expect the curl, okay? That vector is measuring, okay, this propensity to rotate, right? That direction that we're rotating, the magnitude kind of gives us how much, right? The larger the magnitude, much more curl involved. So it's going to really twist. A small value for the curl, the magnitude, smaller vector, and it's not going to rotate that much, right? So I'm thinking about like kind of as this water's flowing, and maybe there's like a rock, there's a post, right, somewhere to tie your boat to, and that water is going to hit, and it's going to start to want to cycle around that post. We're kind of thinking about it like that, okay? So this curl, I get exactly that, how those particles want to twist, rotate about some particular point in space. We have it there, okay? And so that curl of that vector field F, we can compute by taking our del operator and crossing it with that vector field. Okay, so we're going to see we have our I, J, K component. All right, going back to our vector discussions, our del operator d dx, d dy, d dz, our vector field F, P, Q, R, and it's computing that cross product. And so this is how I kind of typically work on it. I recalculate. I think the textbook has the formula, that expansion, right? So in that I direction, cross out that column, that row, it's going to be the partial of R with respect to Y, take away the partial of Q with respect to Z, right? So doing that partial on R, take away partial on Q, then it's always subtraction. And now for the J component, cross up that column or that row, that column, dr dx minus dp dz. And lastly, for that K component, plus there, cross out that column, that row, and this looks familiar with our green stem, right? dq dx minus dp dy, the partial p with respect to y. So that calculation, that cross product gives us this vector, this curl. We can find the magnitude, that direction, to see, right, what direction we're kind of spinning. That water's flowing. That right-hand rule kind of gives us that curl, that direction, if you will, right? And then the magnitude, how strongly that rotation is felt. All right. So there's our curl, that rotational field. And now let's look at the divergence, okay? So for our divergence, think about how we're just interacting that del operator with our vector field F. So the divergence of a vector field F right, this is going to measure, and again, divergence, hopefully, it measures, right, things are leaving, diverging, it's leaving, it measures the net rate of change flowing through a point, okay? So I kind of imagine if we have our space here, and we have some point x, y, z, okay? This divergence is measuring, okay, how swiftly, how kind of this rate at which, if we send particles through that point, is it really going to kind of either force out and spread out away quickly, or is it going to be smaller? And these points are going to kind of pass through nicely, calmly, and not really want to kind of push and force their way out to diverge, right? To escape that space. So with like these, think about like pipes and a lot of pressure of water through, the thinner, the skinnier the pipe, right? At that end point is going to have a lot of divergence that waters really want to spray out. Larger pipes, right? Larger legs, larger bodies of water. As we get down to the opening, as it opens towards the ocean, opens whatever I'm doing, right? If it's a bigger space, it's not going to experience as much pressure, much force of diverging out, spraying out. It's just going to be calmly just trickling in that space. That's kind of divergent, how swiftly these particles are escaping, leaving that particular point in space. Okay, and so for that divergence, of that vector field F, we call it div F, that divergence. And we're going to take this to be the del operator dotted with our vector field. Okay, it's going to be that dot product between. Let's go here, get some green. dx, d dy, d dz, dotted with that vector field p, q, r. So that divergence dp dx plus dq dy plus dr dz. Okay, and that's going to give us this divergence of that vector field. Okay, and again, these are just calculations we'll do to measure that rate at which these particles are escaping or rotating about a certain point in space. Okay, and we'll see these components come up in different aspects of our integrals in vector calculus, transforming that divergence into other operations, a curl, right, to help us sort through, like we did with our Green's theorem previously. We saw that formula similar with our curl, and we're going to start to formulate around those. Okay, all right, so I'll leave it at that. We can look online with some of those lecture slides or example of text of some of these calculations, but hopefully not too terrible in those evaluations. All right.